Welcome back. It's time for another fundamentals video, this one looking at atomic orbitals and phenomena like bonding, non-bonding and hybridization of orbitals. Despite being really fundamental to chemistry, I actually struggle a little bit teaching about atomic orbitals, mostly because when we talk about the probabilities of where an electron might be in an orbital, we stray quite close to physics. And I don't have a lot of training in physics. So what I'm going to be talking about today is mainly the chemistry aspects that you need for understanding chemical reactivity and reaction mechanisms looking at atomic orbitals. So the first thing you need to know is that atomic orbitals will have a phase or phases associated with them. Those phases are typically thought of as being positive or negative, and that sign relates to the solution to the Schrödinger equation, which assigns where the electron could be within that orbital. This is very much a part of quantum mechanics, which itself is a subset of physics. Now, when I think about this positive or negative phase, I typically think about water waves. So if we imagine the water at the beach are the orbitals around an atom, the peaks of the waves, we can consider these positive phases of the wave function, whereas any troughs that you might see, these correspond to negative regions within the wave function. If you have two waves in the ocean with a positive region moving towards one another and they meet, the peaks of those waves are going to overlap constructively. So the wave is going to double in size when they meet each other. This constructive interference will also happen for atomic orbitals if you overlap two orbitals that have a positive wave function. If we imagine in the ocean we have a positive wave, so a crest, and a negative wave, so a trough, moving towards one another, when they overlap, they are going to destructively interfere with one another. So effectively they'll cancel out and you'll see no wave at all at the point whereby they meet one another. That too can be applied to when we overlap two atomic orbitals, one which has a positive wave function and the other has a negative wave function. If you combine them together, they cancel each other out and you get no attractive forces between them. So bringing it back to atomic orbitals, if you have two atomic orbitals overlapping and they have the same phase, it doesn't matter if it's positive or negative, they will overlap constructively and they will stabilize one another. So it will strengthen the attraction between them. Conversely, if you overlap two atomic orbitals and they have mismatched phases, so overlapping a positive and a negative, they overlap destructively. So any attraction that might be there is going to disappear, and there's nothing really holding those orbitals together. So when it's strengthening, we can think of that in terms of bonding. When it's nullifying one another, we can think of that as bonds disappearing. Now, this overlapping of atomic orbitals, it occurs in two places, typically. So it can occur within a single atom as we start adding electrons to the various shells within that atom. So, the 1s, the 2s, the 2p, and so on. The different s orbitals and p orbitals have their own combination of phases that go with them. Because they're all surrounding the same atom, they must by default overlap with one another. The second place where we typically see it is where we bring two different atoms together and bonding occurs. So a bond is an overlapping of atomic orbitals, and those orbitals will have phases associated with them. Now, bonding orbitals will typically have the same phase, whereas if you look at an anti-bonding orbital, they will have mismatched phases. Therefore, there's no attraction between them. So here's just a diagram showing that if we have two atomic orbitals in phase, we get constructive interference. We can imagine this is a positive zone and a negative zone, and we just get larger regions there. If we were to take this negative and positive and completely overlap them together, like in this one, what we get is destructive interference and we get no stabilizing forces, meaning that if they were two different atoms that we're combining together, there's nothing holding those two atoms together and they can drift apart. The first thing we should probably talk about is the representation that chemists typically use for this. Now, so far we've talked about a positive and a negative wave function. The issue that we have as chemists talking about them as positive and negative is that we're usually talking about positive and negative in terms of formal charges. So things being nucleophilic or electrophilic. This is not like that. So if we start talking about orbitals being positive and negative in terms of the wave function, it quickly becomes really confusing in terms of, say, electropositive and electronegative regions, where there is excess electron density or lacking electron density. So to get around that problem, usually chemists don't talk about positive and negative. They colorize the orbitals, with one colour corresponding to positive, the other colour corresponding to negative. That way we're not having multiple different meanings of positive and negative within our molecules. So here, if you see orange, we're talking about a positive wave function. If you see blue, we're talking about a negative wave function. The s orbitals are spherical in nature, and the 1s orbital is the simplest. It's also unique in that it has only one form of wave function. It is a sphere of positive wave function. Looking over here, we've got a graph showing the probability of finding electron as we move away from the nucleus of the atom. And we can see for the 1s orbital, there is one peak with no nodes corresponding to it. So effectively, it's just one big positive region that dissipates as we move away from the nucleus of the atom. That's going to apply for hydrogen and helium. Once we move to the larger elements, we're going to start getting additional electron shells that we need to consider. So if we move on to the 2s orbital, for this orbital, we can see that there's actually two different regions. Inside the core, there is a small region of positive wave function. Around that, there is a node. So that's a region whereby the probability of finding the electron goes down to 0. Once you cross over that node, you get into the larger outer region, which is the negative wave function. If we have a look at the green trace back in our graph, we can see that there is a small region of positive. It doesn't actually show you whether it's positive or negative, so take my word. Small region of positive wave function, a node where it goes down to 0, and then we get this larger, more dominant region of negative wave function as you move away from the nucleus. So in terms of trends, starting from the 1s and moving upwards, we see the 1s has no nodes, the 2s has one node, the 3s has two nodes, and that trend will continue as you move down the periodic table. So much like the 2s orbital, deep in the core, we've got a small region of positive wave function, then a node, then a region of negative wave function, then another node, and then finally we have an even larger region of positive wave function. Again, taking a look at the graph, we can see, yep, small region of positive. The node is in the same places for the 2s orbital. Then we have our region of negative wave function, another node, and then we have our large area of positive wave function once more. So positive, negative, positive. So you can't go from the 2s orbital to the 3s orbital without considering the p orbitals that you need to fill before getting there. So if we consider the shape of the p orbitals, they've got this infinity figure 8 shape to them. If we were to consider where the nucleus of the atom is, it would exist here between the two lobes of the orbital, basically sitting on this XY nodal plane. So specifically what we're looking at is the PZ orbital, and it has a region of positive wave function, and then directly underneath it, it has a region of negative wave function. And if we consider the X and the Y axes, each has its own p orbital associated with it. So just recreate this figure of 8 shape, region of positive, region of negative, and just realign it down the X and the Y axis, and that creates the 3 p orbitals. The PZ, like the one shown here, the PX, which will be the same thing but aligned to the x-axis, and the PY, which again, same thing, but it's aligned to the y-axis. Now, we've talked about hybridizing orbitals a little bit. Now we're going to consider bringing together two atoms. So the nucleus of those atoms is located at the center of this nodal plane, and we're just going to bring these two atoms in this direction, closer together. Now, when we bring together two lobes of positive wave function or two lobes of negative wave function, because they have the same phase, they can overlap constructively. So effectively, the probability of the electron shifts from just being able to inhabit this lobe to be able to jump across and also inhabit the neighboring positive wave function lobe. That happens as well for the negative wave function. And this is what pi bonding really is. It's having two of these p orbitals close by such that the electrons inhabiting them can jump from areas of the same phase and delocalize across multiple different atomic orbitals. So from our molecular orbital diagrams and, the HOMO-LUMO gap, one thing we know is that we can promote electrons into anti-bonding orbitals. Now we're going to consider 2p orbitals that are in anti-bonding mode. And all that means is we're just going to flip the phases around. So now we're bringing our two atoms together. We have a region of positive wave function and negative wave function, and it's coming closer to a correctly aligned p orbital, but those wave functions have the opposite phase. So positive is going to overlap with negative, and here positive is going to overlap with negative. Because these have different phases, the electron can't delocalize across there. So we get no sharing of electrons across these orbitals, and all that means is we have no attraction or stabilization occurring, so that means we're left with repulsion, whereby the two atoms are getting close together to one another. We have electron orbitals that are somewhat negatively charged because electrons are negatively charged. They are going to repel one another. And this is what happens whereby bonds typically break. You populate the anti-bonding orbitals, any attraction they might have had disappears, all you're left with is repulsion between those atoms. So the bonds weaken and the atoms drift apart. If we were to consider the pi anti-bonding orbitals in a bit more detail, we should really consider the repulsion of these orbitals to adopt this shape here, whereby it's not two linear p orbitals. We actually get the lobes starting to bend away from one another to take account for that repulsion. This bent shape is actually kind of important to explain certain chemical phenomena that we might say. So if we have a molecule such as this one thing, if we were to take a snapshot of the molecule, maybe by crystallography, is you would see that these three atoms at the back, they adopt a staggered configuration like this. The reason that they adopt that staggered configuration in relation to the double bond before them is that when the double bond is anti-bonding, the p orbital lobes actually overlap with the sigma bonds behind them. And that additional delocalization locks these three groups in a staggered conformation, like so. Moving on to hybridizing orbitals, looking at the positive and negative wave functions. So hybridization is just what occurs when you start to stack different wave functions on top of one another. We've already talked about if you put a positive and a positive overlapping one another, they're going to constructively enhance one another, increasing the size of that orbital through delocalization. Similarly, if you overlap a positive and a negative wave function, they're going to destructively cancel each other out. So those orbitals are going to shrink in size, potentially down to zero. First scenario we're going to think about is we're just talking about a single atom. So we're looking at the atomic orbitals just surrounding the nucleus of that atom. Now, the two we're going to overlap, we're not going to consider the 1s orbital, we're just going to ignore it, but we're going to combine together the 2s and the 2px orbital. Now, because these both are situated on a single atom, they are localized directly above one another. So as a reminder, the 2s orbital, at its core, it has a small region of positive wave function, and then it's surrounded by a larger region of negative wave function, and it has a single node partitioning those two regions apart from one another. Our px orbital, it has a lobe of positive wave function and a lobe of negative wave function, and our nucleus will be sat between them on the nodal plane. So if we were to shift our 2s orbital directly over the center of our nucleus, so between the positive and negative lobes of the p orbital, and combine them together, what we would get is this sp hybridized orbital. The sp simply comes from we're combining an s and a p orbital together, therefore we're going to get an sp orbital at the end. The 2s orbital, the main component is negative wave function, and it has a small amount of positive wave function at its core. Our p orbital, it's 50-50 split. So it has one lobe of positive wave function, one lobe of negative wave function, and we have equal portions of those together. Now, because our 2s orbital has more negative wave function, we are going to enhance the size of our p orbital like so, and we're going to shrink down the size of our positive wave function lobe. We're not going to completely cancel it out because if we look inside of our 2s orbital, there is indeed a small region of positive wave function. So while we shrink it down, we don't cancel it out entirely. So our sp hybridized orbital, It somewhat resembles the p orbital, but we've enhanced the negative lobe and we've shrunk down the positive lobe. We can complete that. So if this is the 2px orbital, we can do exactly the same thing for the 2py orbital. It'll look exactly the same, but it'll be aligned down a different three-dimensional axis. So if we consider our typical carbon atom, so something that we might see for, say, methane, it has a 2s orbital, it has 3 p orbitals, the px, the py, and the pz. Because we have 1s and 3 p orbitals that we are hybridizing together, what we're going to get is 1, 2, 3, 4, because we're not going to destroy any orbitals somehow. We're going to have 4 lots of sp3. So sp 1, 2, 3. Considering we know the shape of what the hybridized orbital should look like, if we were to combine those 4 sp3 orbitals together in such a way as to provide the orbitals with the most free space, I guess, it's kind of like the experiment where you tie 4 balloons together and you just see what shape it's going to adopt. It's going to adopt this tetrahedral arrangement shown here. Typically, we would think of that in terms of, the blue balloons that we've tied together, but it's also worth knowing that you do have the smaller positive regions sort of fitting in between them as well. This one should probably be orange. I've made a mistake there. That's a positive little zone. That's orange. It's not blue. Okay, next thing to talk about are non-bonding orbitals. These are orbitals whereby the addition of electron density, so you're combining 2 atoms together, but when you combine those 2 atoms together and you get that electron density, it does not stabilize and it does not destabilize. Essentially, nothing really happens upon combining that additional atom into your molecule. So the reason whereby you wouldn't see any change in energy for that orbital is that when you bring the second orbital in together, there is no alignment either in energy or in orientation of the new orbitals that would perturb the electrons in the non-bonding orbital. So a good example of that is the molecule HF, so hydrogen fluoride. We are bringing together a hydrogen atom, which has a 1s orbital, and we're combining that to fluorine, which has a 1s, but it also has the 2s, 2px, 2py, and the 2pz. Now, in this example, the hydrogen is approaching along the z-axis. So if we take a look, if we imagine that this is the z-axis here, when our hydrogen is approaching our fluorine nucleus, only the pz orbital is correctly aligned to intercept the approaching hydrogen s orbital. So what happens is we form our hydrogen fluoride, a bond forms between our 1s orbital and our 2pz orbital. So we get our bonding orbital, we get our anti-bonding orbitals. But if we consider the other 2p orbitals, the px and the py, let's imagine this is the px orbital. The positive and the negative lobes of that orbital are completely in the wrong direction for this hydrogen to really interfere with them at all. And the same goes for the py orbitals. They're just not in the proper orientation that the approach of the hydrogen atom is going to influence them in any way at all. And for this reason, this px and py orbitals, these are non-bonding orbitals. They're effectively lone pairs in the structure. If this is the original energy of the p orbitals, because the hydrogen doesn't interact with the px or the py, they have the same energy and they just sit as they did before. Only the pz is interfered with by the hydrogen. It drops in energy when it bonds. We also get this higher energy anti-bonding orbital associated with forming the molecule. So that's the explanation for non-bonding orbitals. If forming the molecule does not interfere with or impact a molecular orbital in any way, it just continues exactly where it was. You can kind of think of it like a spectator orbital. It's just watching, doing nothing as things happen around it. Okay, now we're going to consider bonding and anti-bonding in more complicated examples involving chains of p orbitals together. So this is obviously quite important for conjugated molecules. There's similar arguments used for aromatic molecules, but essentially what's shown is the trends that you observe as you increase the number of p orbitals chained together. So our typical example of a pi bond versus an anti-pi bond, so this is 2 p orbitals together, they are your options. So if we go and we think about our MO diagram and we think about our bonding and anti-bonding orbitals, we can see that in each of these orbitals, you can stack in 2 electrons. Same goes in this diagram shown here. So if we have our 2 electrons, we're going to put them down here into this pi bonding orbital, and that is what we see. If the pi bond were to absorb energy and go from the HOMO to the LUMO state, one of our electrons will jump from here up to here, and then we're going to have 1 electron bonding, 1 electron anti-bonding, and they're going to cancel each other out. This should be pretty intuitive for you. What if we have 3 p orbitals chained together? Well, in that case, we've sort of got 3 options. We have bonding, whereby all the positive wave function and all the negative wave function are aligned together. We could fit 2 electrons into that. The next one is a non-bonding orbital. So here we have 1 p orbital positive up. We have a p orbital that is non-bonding at all. So for this p orbital, let's imagine that it's positive here, negative here. This positive lobe would stabilize on this side, but it would destabilize on the opposite side. Same goes down here. If the positive lobe is here, it would stabilize on this side, but it would destabilize on the opposite side. So the point is that this one effectively cancels out because it can't stabilize both on either side. It has one half that's going to be stabilized, but it's sort of counteracted by the opposite half, which is destabilizing. Another way you could think about it is it's a p orbital, but it's aligned in a different direction such that it doesn't interact with any of these orbitals at all. Point is, it's a net 0 across this orbital. And finally, if we consider the top example, all of our p orbitals are misaligned. So we have positive, 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 negative, negative, negative. There is no constructive interference to be had at all. This is entirely anti-bonding here. While we're on this example, we can actually have a look at the number of nodes in our molecule as well. Our bottom example will typically have no nodes, but whenever we jump up a step, we're adding a singular node in there. So here we have a node partitioning these 2 ones here. Here we have 2 nodes. So 1 here, 1 here. The node is just an area between which there is no bonding interaction. So these are our examples for 3. Considering we've got 3 p orbitals, let's imagine we've got 3 electrons associated with them. We can put 2 electrons down here, but then our third one will need to occupy this non-bonding orbital here. So what we would probably see is we would have a single double bond in this example, and one of the electrons would not be participating in bonding. It's kind of like this example next door. We've got 2 electrons in bonding, but the third one is not participating in bonding for the molecule. Moving on, 4p orbitals. Bottom example, no nodes. Next one, which is still a bonding orbital, we have a single node. We have 2 pairs. So here we have our positive regions bonding at the top. Next door, after a node, we have the positive regions at the bottom. So this would be a double bond, double bond. Whereas this, we could kind of visualize it as like a huge 4-atom long bond. Moving up, so if we have 1 node here, we're jumping up to the next one, we need to have 2 nodes, so they exist here and here. In this case, the middle 2 p orbitals are bonding, but on either side of them, we've got an anti-bonding interaction here. So overall, 2 anti-bonding interactions, but a single bonding interactions. So the net result would be anti-bonding for that one. Finally, 1, 2, 3 nodes, 1 anti-bonding, 2 anti-bonding, 3 anti-bonding interactions. If we consider that our 4p orbitals have 4 electrons associated with them, we would fill up 2 here, and then we would fill 2 here. So in this case, our HOMO orbital is this one. So what we would see is a double bond, single bond, double bond. If you were to then absorb energy and shift an electron from our HOMO to LUMO orbital, we see that we get a weird change in where the double bond actually exists. So we go from a diene down here to the double bond being in the center. This is actually the kind of transformation that you see in a lot of photochemistry, and reaction will typically occur when we get this jump from pairs of double bonds to this anti-bonding orbital where the double bond shifts around and the 2 termini become reactive. And really, this trend continues with the more p orbitals that you put in our sequence. Just as a reminder, if we're thinking about chemistry and reactivity, we're generally only considering the HOMO and the LUMO gap. So usually it's somewhere like, situated here in the middle. We're never really, okay, except for this one, For these examples, we're never really considering the bottom. We're never really considering the very top. We're looking at where the electrons can jump up and come back down like so. So to just give you some examples of how atomic orbitals can interact, we're considering a chain of 3 p orbitals, and we're just adding different numbers of electrons into those 3 p orbitals. One thing we saw from the previous slide is that when you combine these 3 orbitals together, you get a bonding, non-bonding, and an anti-bonding orbital. As you'll know from MO diagrams, if we know where these are approximately placed energetically, we're going to fill our electrons starting from the bottom and moving upwards like so. So for our 3 p orbitals, we're going to have 2 electrons in bonding, 1 non-bonding, and then we're basically done at that point. We can think about things like, okay, what if we start adding more or taking electrons away from these orbitals? So if we subtract a single electron from our 3 p orbitals, we're going to eliminate our highest energy electron, and we're left with 2 in the bonding orbital. So that's our bottom example here. We have our pi bond here. We've lost an electron, so we've got a positive charge. One thing you can see is that the electrons in this bottom orbital should be delocalized across all 3 of the p orbitals. So realistically, we should draw this double bond as being delocalized across all 3 carbon atoms. So we'll be shifting the positive charge across, we'll be shifting the double bond across, and that explains what occurs in that situation. For the situation that's actually shown, 3 electrons, we can draw that. So we have our pi bond, we have our singular electron, which is a radical species. We can put our radical inside our non-bonding p orbital. You can see that there's 2 on either side. So again, this is going to be delocalized. You can draw this structure in this way, or you can shift this single unpaired electron across to the other p orbital, and we will shift this double bond over to the other side. Finally, if we were to add another electron into our MO diagram, it's going to occupy this orbital, so then we'll have a spin up, spin down electron. Again, we know where these 2 orbitals are, so we're going to place our pair of non-bonding electrons on either this carbon or this carbon. And again, it's delocalized across the molecule. We can have our pi bond situated here, or we can shove it onto the other side, put our negative charge onto this side, so our lone pair would be here. You could keep going if you wanted. You could keep adding more electrons, and then we're going to start adding them into the anti-bonding orbitals. So that would actually start to weaken the pi bond, and it would disappear. So what about the sigma orientation of our 3 p orbitals? Well, in that case, it's the same as before. We've got our bonding, so we have our 1, 2, 3 atoms together. Bonding's going to be positive to positive, negative to negative, so everything is bonding all the way across here. We can have our non-bonding example. So if we imagine there was a positive lobe in this direction, that would be bonding, but then we'd have a negative wave function overlapping a positive wave function, so any benefit would cancel out one another. And then finally, anti-bonding. Okay, all of the positive wave function is aligned to negative wave function all the way along. So effectively, there is no stabilization at all. It's all repulsive, basically all good, net zero, all bad. What if we have 2 p orbitals and an s orbital? Well, same as before, we can have our s orbital. So let's say it's the 2s, so it's mostly negative. Then we have our negative lobes pointed towards it. Remember, the colors are arbitrary. I'm just making this up as we go along. If we were to place this orbital inside between these 2, it would stabilize on this side, but it would be destabilized to an equal extent on the other orbital on the other side. So net zero in the middle. And then finally, we have, let's imagine, okay, negative, positive, positive. So it's completely destabilizing over here. Final example, we need to consider aromatic p orbitals. In this situation, the sp2 carbons all have a non-hybridized p orbital in the same plane. So effectively, all of these p orbitals are aligned such that they can overlap or delocalize. Each of these p orbitals contains a single electron, and we have different combinations of phased p orbitals that either bond or anti-bond. So here we have our examples. So if we have our 6 2p orbitals, that means we have 6 electrons to play with. We can have all of our p orbitals in exactly the same phase. All the positives and all the negatives are aligned together. Then we can move up, whereby we have is that like a C2 inversion plane or a mirror plane? I don't think it's a mirror plane. Anyway, there is symmetry running down the middle. So we have our, let's say, negative lobes at the top here, positive lobes at the top here, negative lobes at the bottom, positive lobes at the bottom. So we have these three carbons constructively combining together. We have a nodal line running through the molecule, and then we have these three carbons constructively supporting one another. So that's one example. The other thing is we have two non-bonding on the ends and two pairs of constructively interfering carbons on either side. Anything below this line we consider to be bonding. Anything above the line we consider that the bulk of the interactions are anti-bonding. So looking at the anti-bonding, at the very top one, all of our p orbitals are anti-bonded to every single one alongside it. So this is completely anti-bonding here. For these two examples, okay, we've got two pairs that appear to be bonding, but on either side, so we've got anti-bonding, anti-bonding, bonding, anti-bonding, anti-bonding, bonding. So more anti-bonding than bonding interactions. So the overall influence we see is anti-bonding. Here we have two pairs of anti-bonding and two non-bonding. We can see the associated energies with these orbitals. 100% bonding is at the bottom, as we would expect. 100% anti-bonding is at the top, as we would also expect. If we tally up the number of bonding interactions that we have here, it's sort of two pairs, I guess. So we give these equivalent. Take my word for it, these two are equivalent as well. So if we start filling up our orbitals using our 6 electrons, 2 go here, 2 go here, 2 go here, and the overall net result of that gives us our aromatic ring that we're all familiar with. So a hexagon, 3 bonding interactions between it, and they are all kind of delocalized, sort of, the double bonds are moving around the ring in a resonance structure. Just a few examples of how these orbitals come into play for certain kinds of chemical reactions. We can look at the SN2 reaction, which is the backside attack from a nucleophile on an electron-deficient atom. So in this reaction, we have a carbon to bromide bond that needs to break. Because that bond needs to break, we can draw the anti-bonding orbitals for it. So this is our LUMO interaction, and we've drawn the sigma anti-bonding orbital arrangement shown here. Our nucleophile has a lone pair. That would be the highest occupied molecular orbital, or the HOMO orbital. When we draw out these orbitals, we can see why it needs to be a backside attack. If we look at our anti-bonding orbitals, we've flipped around our sp3 hybridized orbital, giving this big lobe of, let's say, positive wave function. Our nucleophile comes in, which has a matching region of positive wave function, and these can then constructively overlap and combine together to give a new bond. So effectively, the orbital of the nucleophile is stabilizing the anti-bonding orbital in the transition state. Because this anti-bonding orbital is being stabilized, the attractive force holding the bromine and the carbon together effectively nullifies or disappears. The bromine is going to leave, while a new bond is going to form here. And that's indeed what we draw. This is our transition states. So electrons are coming from the nucleophile to the carbon. The electrons in this bond are going to move across to the bromine, which is going to move away as the leaving group. This is going to result in an inversion of stereochemistry, and that has to occur simply because this nucleophile needs to come in at this 180 angle, which is going to flip the stereochemistry for these 3 R groups as the bromide leaves the reaction. So you might think, well, why can't the nucleophile come in from a different angle? So if we've drawn out our anti-bonding sigma bond orbitals, shown here, we can see that there is a region of, let's say, negative and positive. If the nucleophile was to approach from below, which would preserve the stereochemistry on the carbon, any stabilization that might occur between matching wave function is going to be negated by the equal amount of mismatched wave function there. So the nucleophile cannot come in from this orientation because effectively this is a non-bonding interaction. Any stabilization you would get by combining the same phase of wave function is equally providing a destabilizing interaction. So the net overall is nothing. You can't form a bond by the nucleophile coming in from the bottom. It can only come in this direction and overlapping this lobe of the sp3 orbital. you can't attack these two oppositely phased regions at the same time. You get an overall no net attraction, which means no bond is going to form. But what about electrophilic substitution reactions? These can actually occur with or without inversion of the stereochemistry. So effectively what we've done is we've swapped around the HOMO and the LUMO in this case. So in one situation, our electrophile can approach in the same way as for the previous example, so via a backside attack, and this is going to give you an inversion in stereochemistry. So in this case, the empty orbital of the electrophile, which is the LUMO, it approaches this small lobe of the sigma bonding sp3 orbital. It can stabilize and form a new bond here, thereby weakening this bond, and ultimately this M group would be eliminated. So we can think about that in terms of the electron density that's typically localized here is drawn in this direction to stabilize this new bond, and this M group is going to be an electron deficient leaving group. However, equally, we can preserve the stereochemistry. So in this case, we've got our empty orbital of the electrophile, and it's going to approach from the bottom. So the electrophile is the LUMO. The highest occupied molecular orbital is going to be this bonding orbital between the carbon and the metal. And in this case, the electrons are going to be drawn downwards into this empty orbital, leaving our metal, which is going to be our leaving group, having had its electrons stolen. So these are the two transition states that can occur for an electrophilic substitution. We can get a backside attack occurring, which swaps the electrochemistry around. But because the HOMO and the LUMO have been swapped around, we can also get the electrophile approaching below the bond, giving us this sort of triangular transition state. And that preserves the stereochemistry around the carbon. Last thing to quickly touch upon are pericyclic reactions. We did briefly talk about the 4 aligned p orbitals shown together, and how typically these would have 4 electrons, so 2 here, 2 here, making this the HOMO orbital and this the LUMO orbital just above it, going from bonding to antibonding. If we consider this reaction, it's a photochemical reaction. We can consider the orbitals for the starting material. Here you can see the 4 orbitals, which correspond over to these 4 orbitals here. We've drawn out the way that the molecule exists in the HOMO state, with a double bond here, and a node between them, giving us this double bond, double bond conformation. If this orbital was to absorb the energy of a photon, what's going to happen is an electron is going to jump from this orbital up to the orbital above it. So we go from a bonding up to an anti-bonding arrangement, shown here. That's going to change the arrangement of our double bonds. So in this case, instead of having 2 double bonds adjacent to one another, it changes to having a single double bond here, and we consider there being an unpaired electron here and an unpaired electron here. These terminal carbons are now free to rotate, which they do, and as they rotate around, we can get constructive overlap between the lobes with the same phase, generating this bonding interaction shown here. So ultimately, upon absorbing this photon of energy, we get the conversion of our diene across to this square molecule. And because we know the phase of the orbitals down here, and we know that to get this constructive overlap, they have to rotate outwards, like so, we can actually predict the stereochemistry of our products. So we have stereo control over this reaction as well, because this is the only orientation that's going to give you this constructive overlap of the 2 orbitals shown like so. So to summarize, you can combine in phase, either positive or negative orbitals, which results in constructive interference and stabilization of those orbitals. Because talking about positive and negative wave functions is kind of confusing for chemists, when we're talking about electropositive and electronegative things, typically you'll see them as differently colored orbitals, not drawn as positive or negative. If you combine orbitals with mismatched phases, you get destructive interference, which nullifies any stabilization, leaving you with nothing but interatomic repulsion, i.e. breaking of bonds. There are such a thing as non-bonding orbitals. That occurs when you bring 2 atoms together, but that event doesn't perturb the orbitals in any way, usually because those orbitals are oriented away from the incoming atom. Lastly, understanding the HOMO LUMO interactions, allows you to explain how and why chemical reactions occur. Things like why backside attack is going to be favoured, preserving stereochemistry, or why pericyclic reactions occur for conjugated p orbitals. Well, that's it. I hope that was useful. Thanks for watching.